Alright, so we're going to get deeper into the probability rules. We're going to get really good at doing basic probability today. Alright, rule number 4, basically this is where we start getting to being able to do advanced stuff. The sum of the probabilities of the outcomes in the sample space is 1. That is really simple, really basic. You're going to forget about it. Usually when we start doing really advanced stuff. This guy right here, super, super, super important to think about and remember when you don't want to remember it. Alright, we're going to use that along with complements of events. By the way, complement is when you say something nice, right? The complement is the exact opposite, which does not mean it's saying something mean. It means it's not that thing. So the complement of 3 would be not 3. That's not good. The complement of good is bad, right? It's whatever's not part of that. And we have a couple different ways of making a symbol for that. The first one is, so this right here is the probability of A, right? The complement of that would be the probability of not A, or it could be the probability of a complement, which would also be not A, or you could write it as the probability of a complement like that. Any three, if you try going to YouTube or a different textbook or looking things up online or college or anywhere you go, it can be written as those. That's not a negative sign. In fact, sometimes they put a little guy after it like that to make it note that it's not that. They're all going to have one that they really like and they say this is the it. In this class, because I've had like 2 textbooks in a row that do it, that's how we're typically going to do it. Every now and then you'll see something that has it written differently. From me even. But that's our go-to, meaning the complement of A. Alright, now, really, really, really cool formulas, right? The probability of A plus its complement is always going to be 1, right? Because everything's either going to be A or it's not going to be A. And since the sum of everything is 1, we have that. You can build 2 other rules based off of that, right? I can solve for the probability of A. How much space do I have? Okay, this is not bad. That would mean the probability of A is going to equal 1 minus its complement, or the probability of the complement of A is going to be 1 minus the probability of A. Alright, you gotta get used to this function notation stuff. You saw it in Algebra 2. If you took Algebra 2, you saw it in Algebra 1, but not very much. Really, really useful and important when we start writing these formulas. The probability of a thing happening plus the probability of the a thing not happening is 1. And you can use basic algebra to get either of those. This one right here is probably the one that's used the most. Usually, if what you're looking for, A, is hard to calculate, it not happening is easier to calculate. And if it's easier to calculate it not happening, you just do 1 minus that thing. Alright, we're going to hit some practice problems really quick. So, the complement of rolling a die and getting a 4, that would be rolling a 1, a 2, a 3, a 5, or a 6, or basically just not a 4. Right? Either of those would work. Probably selecting a letter and getting a vowel. That'd be selecting a letter and getting a consonant that I can't spell right now, so I'm going to skip it. You know, B, C, D, F, G, H, I, J, K, L, M, N, P, Q, R, S, T, V, W, X, sometimes Y, and Z. I'm not really sure what to do with the Y there. Just going the opposite. Selecting a month, and it begins with J. That would be any month that doesn't begin with J. So that'd be like February, March, April, May, August, September, October, November, or December. Right? Anything other than that thing you're asking about. second day of the week and getting a weekday, that would be, hey, weekend. Basically not a weekday. Although y'all gonna have like first spring break soon, and then you'll be like it's something completely different. All right, ready? Here's some fun examples. I lost my spot. All right, if the probability that person lives in an industrialized country of the world is 1/5 or 1 out of 5, what's the probability of its complement? I'm going to do this slow, even if you get it. So the probability of the complement of A is 1 minus the probability of A. A being 1/5. Now, some of y'all see fractions, and you see subtraction without a common denominator, and you automatically freak out. Don't automatically freak out, okay? 1/5 plus how many fifths would make it a whole. That's the exact same formula, exact same thing. I just switched it around. It's always going to be the less. The complement is bottom minus top. That's easier for you people that don't like stuff. Over the top. So the probability of the complement of A is the bottom of A minus top of A. This is if you have the probability of A in a fraction. All over the bottom of A. Alright? So if the probability of A is 1 out of 5, I do 5 minus 1 is 4 over 5. That's like the easy, fast way. If you don't like that, learn how to deal with fractions. Alright? That's the basics for complements. They're really simple. They're simpler right now. They're going to be used. Still be as simple. They're not going to be complex. But they're going to be used to like really make a lot of advanced stuff way easier. And so much so that you'll see a hard problem that you like will get stuck on and be like, I can't figure this out at all. And I will say, we'll just use the complement and we'll do it in like 2 steps. Really becomes that useful for things that we otherwise wouldn't be able to calculate. Alright, now, last new thingish, the empirical probability. Alright, this is so far we've been doing classical probability where it's just the things. Now, we've touched a little bit of empirical. Alright, empirical probability uses frequency distributions or samples. The probability of an event is going to be its relative frequency from a frequency distribution. I believe that's getting ready to be like a practice quiz answer saying, yes, I read my notes. The probability of event E, using empirical probability, is its relative frequency. Remember relative frequency, we did that before. That is frequency divided by the total sample size. That's a little redundant, but there it is. It's how many times something happened divided by how many times you tried. Really, really useful. It is based off of previous samples, but I mean you had to have had the sample in the past at some point. But that's what you use your past samples. It uses empirical probability goes off of the basis that the past will tell you about the future. All right, or you do a bunch of samples, you see how often something happens, and you say that's the chances of it happening. Really cool. All right, so we have this chart here. People were trying out a soft drink or something like that. You see the notes that has it in there with all the details, right? And they asked them if they liked it or not. 15 of them said yes. 8 of them said no. 2 of them said they weren't sure. They couldn't make up their minds. And there were 25 total people. And this is all empirical probability, all right? The probability that the person said no is 8 out of 25. 8 out of 25. Make sense? It's just how many times it happened divided by the total. The probability that they said yes, 15 out of 25. Now, I am going to reduce because I can, right? 5 goes into both of those. 15 3 times, 25 5, and I have 3/5. Anytime I can reduce, I should reduce. Reduce, reuse, recycle, save the planet. All right. The probability of the complement of no. That means the probability they did not say no. So 15 of them said yes, and these two others that were undecided, they also did not say no. That's 17 out of 25. All right. It's also the 25 total minus the 8 that said no, leaving 17 others. Luckily 17 is prime, so I don't have to do that. And the probability they were not, notice this complement sign up here, probably they were not undecided. That is, well, there were 2 that were undecided, right? 25 minus 2 is 23 out of 25. Yay! All right, we now have the last problem. Yeah, it's my last board, so it's the last problem. In a sample of 50 people, 21 had type O, 22 had type A, 5 had type B, and 2 had type AB. All right, we're finding the probability. Notice I'm reading from the symbols so you can have practice. Probability the person had type O blood. Probability of an O. That's not 0. That's type O blood. That's 21 out of 50, which does not reduce. Probably they had type A or B. 22 had type A. 5 had type B. That's 27 total people out of 50. Probably they did not have type A, and they did not have type O. Great. So 21 had type O, 22 had type A, right? So that's 43 people total. So we had 43 out of the 50 had either of them. What, 7 people did not have either? 7 people that were not type A, and they were not type O. Right? We're going to get to this. This one is worded kind of tricky. We'll fix it. We'll make it better. Probably they were not, see the not symbol? Probably they were not type AB. There were only 2 of them. 2 out of 50. Now watch this real cool thing. 2 out of 50 is going to reduce to 1 out of 25. So bottom minus top, 24 out of 25. Alright, it automatically, if you reduce, the cool thing about probability is if it reduces in one spot, it's going to reduce in all of the spots. You might not believe me, I don't feel like showing the proof, just watch. It'll happen. And when you figure it out and you see it happen all the time, you'll either be amazed or you'll say, well, yeah, because Junwei told me that. Not a big deal. All right, last 2 things. First is the law of large numbers. It's really important for empirical probability. It lends us credence or not. I'm not really sure which. Law of large numbers. Okay? It means, it says, as sample size grows, empirical probability approaches or gets closer and closer to classical probability. Alright? Basically says if I keep on asking people over and over and over again, I'm eventually going to get whatever I was going to have as results for classical. This saying it holds true or a word? I don't know. This is easier to see and grasp, and it's easier to prove with inanimate objects, like rolling a die. If I keep rolling the die over and over and over and over and over again, eventually I'm going to have every single number is going to pop up 1/6 of the times. It's just in there. We're going to use it. Basically, we're going to use this law to eventually show that if we have large enough samples, we know what the answers are going to be, and that we'll know what these are by taking lots of samples. It's going to be used a little bit. It has to get mentioned. We're going to really put it into practice in some later chapters. All right, and the very last thing is subjective probability, which we do not use in this class. Do not use. All right, the public news media likes to use it. It's basically, usually it's an expert's opinion where they just say this is what I think is going to happen, but a lot of times it's not even an expert. Subjective probability is anytime you get somebody's opinion. All right, they don't go back and do a bunch of data for it. They didn't do the classical numbers. They just do a number off the top of their head. And that is actually what happens, sadly, more often than not. But we will not do it in this class. That's also a quiz question coming up in the Google form that you're going to click on. I know you are, so otherwise you won't get any credit. All right, but we are not using it at all. It's kind of a trick question. It's just some expert's opinion, even if it's not, and sometimes it's not an expert, but usually it's an expert opinion. All right, have fun. Hopefully I'll get to see you again soon.